Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is the DC power supply. Our objective today is to review voltage, discuss ground as a common frame of reference, and learn to use a basic DC power supply with or without a ground reference. Additionally, we'll discuss the differences between constant voltage mode and constant current mode for DC power supplies. Since the topic of DC power supplies is inextricably linked to that of voltage, let's discuss our concept of voltage, where voltage is a potential difference observed between 2 points. Voltage is measured across something, where one point is measured with reference to another. The phrase "with reference to" means here is the point I am comparing all other points to. If you wish to be strictly analytical about it, the unit of volts is a derived unit, where 1 volt is equal to 1 joule per coulomb, meaning a specific quantity of electrons, the coulomb, has more or less energy per coulomb between two measured points. One point could have 20 joules per coulomb, and another point could have 8 joules per coulomb. Yet another pair of points could have a point at 100 joules per coulomb, and the other at 88 joules per coulomb. For both pairs of points, there is a 12 joule per coulomb or 12 volt differential between the points, and current will move between the points if a conductive path exists. The amount of current moving between the 2 points is directly proportional to the voltage differential between them and inversely proportional to the resistance of the conductive path via Ohm's law. Perhaps you've heard of it. In this case, the voltage differential between both sets of points is the same, and we could expect to observe the same current through identical resistive paths. This analytical unit derivation exercise sometimes doesn't cut it for people, so I'm going to briefly step out of the real world and dive into analogy land to discuss this concept in further detail. Analogy land is a lush wooded plain surrounded by hills and frequent wells from which the populace draws their water. If you are on the plain, which I'll call the ground plane for obvious reasons, the hill is higher or more positive than your reference position, and a positive differential between the ground plane and the hill exists. If something was on top of the hill, it would roll down to you. If you're on the ground plane and look into a well of equal depth as our first hill's height, the same differential between your reference plane and the bottom of this well exists, only this time it's negative in magnitude. If something was on the ground, it would roll into the well. A differential between the reference position and these other points exist in both cases. Now, consider a change in reference. If you are at the bottom of the well, ground would be higher or more positive than your reference position. The top of the hill would now be doubly as high as your reference position because the distance is twice as great. Ground means nothing to you if you're at the bottom of the well and your intended goal is the top of the hill. Ground is just something you pass on the way up. Consider yet another change in reference. You could be at the top of the hill looking past ground into the bottom of the well. The distance would again be twice as great, only negative in magnitude. Again, ground means nothing to you if you're at the top of a hill falling into a well. Ground is just something you pass on the way down. If the ground plane serves no purpose for the measurement of differential between 2 points, why do the people of analogy land employ it as a frequently used reference point? Because people live on the ground. They don't live in wells. They don't ordinarily live on the top of mountains. They live on the ground. You may as well reference any differential from where you live. Think about it. Mountains are usually referenced from mean sea level, and Mount Everest is considered the highest mountain. Mauna Kea is understandably pissed about this arrangement because if measured from its oceanic base, it's more than twice as tall as this pipsqueak. Too bad, Mauna Kea. I know Aquaman and his girlfriend, the Little Mermaid, think you're the tallest mountain on Earth, but we don't. Stepping out of analogy land, realize a voltage differential can exist with or without a ground reference. The schematic symbol for ground, sometimes called PE or protective earth, is this kind of rod-like thing that looks like it's stuck in the mud. That's really what it is if you've ever witnessed a house or a building being constructed. If there is a ground symbol on a schematic, it indicates that that point is at the same potential as the stuff you're standing on, obviously barring special case scenarios such as insulating mats and the like. For measurement purposes, the Earth serves as a reasonably constant potential reference against which other potentials can be measured. An electrical ground system needs to have an appropriate current carrying capability to serve as an adequate reference level. Consider ground references for automobiles or portable electronic devices like your cell phone. They're not really hooked to ground via an electrical path. However, the frame in the case of the automobile and the circuit board upon which the cell phone is built is large enough to serve as this purpose. In automobiles, this is sometimes called a chassis ground and symbolized with something that looks very similar to a ground. Circuit boards have a digital ground, symbolized by an upside-down triangle. There can be differences between systems employing a chassis ground or a digital ground and that of regular ground. In electronic circuit theory, a ground is usually idealized as an infinite source or sink for charge, which can absorb or supply an unlimited amount of current without changing its potential. This ideal scenario breaks down when a ground connection has significant resistance and this approximation of zero potential is no longer valid. An electrical circuit can exist with or without a ground reference. And what's shocking, pardon the pun, our ground reference can exist in many different places within a circuit. Consider this circuit with a 12-volt DC source supplying current to a resistor. There is no ground reference. In this case, the positive terminal is simply 12 volts higher than the negative terminal. In order to measure the potential difference, I'd have to physically place my reference lead upon the negative terminal of my source or the negative terminal of my resistor and take the high lead of my voltmeter and touch either the positive terminal of my source or the positive terminal of my resistor. The difference exists between these two nodes only, and the difference is without consideration to any outside reference. If we're to use an example within analogy land to describe these type of circuits, this is like the differential between two hilltops, two wells, or between that of a hill and well. In all these cases, there is a ground reference plane. It's just not being employed as a reference. What's even stranger, this could also represent the elevation difference between two terrain features on analogy land's moon or a planet light years away, something totally without reference nor in any way connected to analogy land. The point is, differences are between 2 points and can exist without reference to a ground plane. If I was to include a ground reference node, in this case hooked to the negative end of my DC power supply, the positive terminal would still be 12 volts higher than the negative terminal. The only difference between this and our original circuit being that the positive terminal is now 12 volts higher than what you are standing on. Because the differential exists, conventional current emanating from my positive terminal travels to my negative terminal, and this is where it gets weird. Because the negative terminal is hooked to ground, current will travel anywhere ground exists, meaning the whole ground plane could theoretically be your return path. This sometimes vastly simplifies complex schematics. I know it does not look like there's a complete circuit, but realize those two symbols imply a single point of common connection. That point of common connection being the whole ground plane. For those of you with a hydraulics background, this might be similar to the return tank connection. No sense in drawing additional wires or hoses all going back to the same place if there exists a schematic symbol for that single common destination. Beyond simplifying schematic drawings, if I took my reference probe and placed it on a point hooked to ground, even if it wasn't directly inside my circuit, I could now measure differential from ground with only the high lead of my voltmeter. Not only does this vastly simplify schematic drawings and voltage measurements using common points of connections and frame of reference, it has important safety considerations too. We'll deal with the safety considerations of ground connections when we discuss grounding and bonding and circuit protection devices like fuses, circuit breakers, and ground fault current interrupters in the Series DC Circuits lecture. Right now, I just want to introduce ground's usage as a common reference. Consider another permutation of our basic circuit, this time with ground hooked to our positive terminal. You might think this is a dangerous location to do so, but please avoid this instinctive reaction. Ground, again, is just a point of reference and has nothing to do with the negative terminal of a voltage source. In this case, the positive terminal is now at the same potential as our reference plane, but the negative terminal is now 12 volts below that of our reference plane. This is akin to the differential exhibited between the ground plane and a well in analogy land. Things can fall into the well because there's a difference. Gravity still works in the same direction. In this circuit, charges will still move because a difference still exists. In this case, any conventional current emanating from our positive terminal, or for that matter, ground, since they're both at the same potential, travels to the negative terminal of our voltage source because the positive terminal and ground are still 12 volts higher than the negative terminal. Or if you want to think of it this way, the negative terminal is 12 volts lower than ground, i.e. a 12 volt differential still exists. In this case, the direction of conventional current travel is the same. In fact, pretty much everything is the same, except the differential is just exhibited on the other side of our common frame of reference. It's okay to do this. This being said, it's not normally done this way. Most systems, if they include a ground reference, do so on the negative terminal of the source. Positive ground and even central ground systems exist. There's no law saying that you have to be readable, consistent, or understandable. Surely half the problems in the back of electronics textbooks are just simple circuits purposely trying to look goofy and hard to read. I am not trying to softball you when I routinely present sources on the left-hand side with a positive terminal pointed up, the negative terminal pointed down, and if I incorporate one at all, a ground reference on the negative terminal. You can do it any way you wish. As long as there is a differential between 2 points and a conductive path between these 2 points, conventional current will flow from the positive terminal of a source to the negative terminal of a source. Sometimes it flows clockwise, sometimes it flows counterclockwise, and sometimes it doesn't flow at all. By routinely placing my sources in this manner, I'm just trying to be readable, consistent, and understandable. There will be more than enough time to chase as many rabbits down as many different holes as we wish. For now, such goofy obfuscations only muddle the basic concepts I'm trying to present. Let's stick with the basics before we try to get tricky. This being said, let's take a look at these different circuits and see if you can determine which direction conventional current will flow, if at all. Remember, ground is a common frame of reference and often doubly serves as a common point of connection. Pause the lecture and take your best shot. Fair warning, some of these are pretty goofy and may require some thought. Okay, here's our rogues gallery of goofy circuits. Again, what I'm asking you to do, see if you can determine the direction which conventional current will flow, if at all. If current does flow, indicate the polarity of the voltage drop. Pause the lecture and take your best shot. Again, fair warning, some of these may require some thought. The one in the upper left should have been incredibly easy. All it is a 12 volt source without reference to ground. Conventional current will travel clockwise out of the positive terminal of our voltage source into the negative terminal and induce a voltage drop across our load resistor with the indicated polarity. Our second one is the same song in reverse. It's the same circuit with the voltage source on the right-hand side. In this case, conventional current will come out of the positive terminal of the voltage supply and return to the negative terminal and travel in a counterclockwise direction and induce a voltage drop with the following voltage polarity. Third one is more the same. It's a 12 volt source without a ground reference. That being said, there is still 12 volt differential, and conventional current will come out of the positive terminal and travel to the negative terminal and induce a voltage drop across our load resistor with the indicated polarity. The fourth one incorporates a ground reference and a switch. With a ground reference on the negative terminal of our voltage source, we realize that the positive terminal is just 12 volts higher than this reference. With an open switch, however, no current can flow, because an open switch is ideally an infinite resistance. However, when the switch is closed, current can travel in the indicated direction and induce a voltage drop with the indicated polarity. Notice that the negative terminal of the resistor is also at ground. For all intents and purposes, I could redraw the circuit in the following fashion. it looks like there is not a complete circuit. However, realize those two ground schematic symbols are not independent nodes, but the same ground node. If it helps you think about it, quite literally visualize the ground being a portion of the circuit. Our fifth example in the lower left-hand side is, for all intents and purposes, the exact same circuit in the upper right. There's a 12-volt source with a ground reference on the negative terminal, meaning the positive terminal of that source is 12 volts higher than ground. The open switch will not allow current flow to our electrical load. In this case, however, the load resistor has simply been swapped out for a motor. When the switch is open, the motor won't run. When the switch is closed, the motor will run. This is known as a high-side switching arrangement, and the fact that the switch provides the supply voltage to the motor. Compare and contrast this to the relationship right next door. This is a low-side switching arrangement. For all intents and purposes, it does the same thing. It's a 12-volt source where the negative lead is tied to ground. The positive lead is therefore 12 volts higher than ground, and that is connected to the motor, and the motor is connected to an open switch. When the switch is open, current can't flow, and the motor won't run. When the switch is closed, it simply provides a path to ground, and the motor now runs. For all intents and purposes, the low side switch is acting exactly the same way as the high side switch does. The only difference is that it provides a path to ground. The high side switch simply provides a path of connection to the source. Compare and contrast these two methodologies. In the case of the high side switch, our motor is connected to ground, and the switch simply enables it by connecting it to a voltage source. Hence the alternate term for this methodology, sourcing. In the case of the low side switch, the connection to the supply exists. The switch's only purpose is to provide a path to ground, and this is sometimes known as a sinking arrangement. Let's reopen our switches for both a high side and low side switching arrangement and insert an additional element in series with our switch and motor. In this case, these are both fuses. I know we haven't gone over the details of fuses yet, and we will do so in the very near future. But for right now, understand that a fuse is a circuit protection device. And in the event current flow exceeds the fuse's rating, the fuse simply melts and becomes an open circuit. Now, with this additional fuse element in play, consider the safety aspects of both high side and low side switching. What would happen if an accidental ground connection in the form of an errant wire or connection with a frame occurred on one side of the switch? If the switch was closed, what is the resistance for the high side switching arrangement? In this case, it would be 0 ohms of resistance, because all three of those ground symbols really are kind of a single point. Yes, with a 0 ohm path, current would spike to an incredibly high value, but this negative effect is handled by our circuit protection device, the fuse. When current in excess of this fuse's rating is experienced, it simply melts and becomes an open switch, stopping current. Look at our motor. At no point did our motor ever start because of this accidental ground connection, because each terminal is hooked to ground, and no differential ever occurred across it. Consider the exact same scenario for a low side switching arrangement. In the event of an errant connection to ground, on this side of the switch, there now exists a path for current, despite the fact that the switch is open. Because again, despite there being 3 separate symbols, it really means that those are all pooled to one point of common connection. The errant connection to ground is providing a path to ground for this motor, and the motor could start unexpectedly in a low side switching arrangement. Again, current is well within the operating parameters of this fuse, and the fuse will not blow. And a motor configured in a low side switching arrangement could unexpectedly start. We'll return to this subject in the near future when we discuss series circuits in both the switches in series lecture and circuit protection devices. But for right now, you should understand that a high-side switching arrangement is using the fuse and the existence of a ground connection to make sure that the motor doesn't start unexpectedly. And a low-side configuration, an accidental ground connection, can accidentally start motors. It's for this reason high-side switching arrangements are preferred to low-side switching arrangements. Okay, moving on. Our next example shows two opposing voltage supplies, both referenced from ground using the negative terminal. Visually, one could think in this manner. Start at ground, go up 12 volts. Start at ground, go up 12 volts. What is the differential between the two terminals of this resistor? If it's 12 volts on one side and 12 volts on the other, there is no differential between the two terminals and current will not flow. Consider this slight modification, where one voltage source is 12 volts and another voltage source is 6 volts. Using visual means to present this, start at ground, go up 12 volts. Start at ground, go up 6 volts. In this case, there is a 6 volt differential, this side being more positive, this side being more negative, and conventional current will flow in this direction. It looks like these sources are fighting each other, and in fact they are. This is an opposing relationship. You need not think of this as a conflict though. Think of a simple application for such an arrangement in the form of a battery charger, where the source on the left is reversing current flow into the source on the right and charging it back up. If we were to reverse the magnitudes of our opposing devices, current would flow in the opposite direction and induce an opposite polarity drop. Finally, consider our last example problem in the lower right-hand corner, where these devices seem to be aiding one another, and in fact they are. One device's negative terminal is hooked to ground, and from ground, we go up 12 volts. Now this device's negative terminal is hooked to 12 volts, and it's going up an additional 12 volts for a rise of 24 volts referenced from ground. If the right lead of our load resistor is hooked to ground, conventional current will travel in this direction and induce a voltage drop with the indicated polarity. This is a series aiding relationship, where one voltage source's negative terminal is simply referenced from another source's positive terminal, in effect increasing the available voltage. Okay, that last half may have been a little tricky, but don't tell me I didn't warn you. We are definitely going to revisit these topics when we discuss series circuits, including high-side and low-side switching arrangements, circuit protection devices, series opposing, series aiding voltage sources, and Kirchhoff's voltage law. Moving on. All right, I believe we've covered enough conceptual material about voltage and ground references to introduce a DC power supply and start fiddling with the knobs. We're going to use the Tenma triple output DC power supply 724045A as a teaching aid. This lecture is not meant to be a review nor a thorough analysis of this DC power supply. Additionally, in no way, shape, or form am I recommending this manufacturer over others, nor am I recommending this particular model. I'm pretty sure they don't even make this model anymore, so good luck finding one outside of eBay. Either way, this model has exactly what we need to discuss basic DC power supplies. Your DC power supply might be different than this one, and it's your responsibility to learn how to safely operate your DC power supply. Most questions or concerns about your DC power supply are typically addressed by reading the fine manual that came with your DC power supply. Again, my intention in this lecture is just a brief orientation of DC power supplies. We'll return later for some experimental verification lectures where the DC power supply is used to demonstrate circuit level properties. Before it is used in this capacity, I just want to take a look at it, fiddle with some knobs, push some buttons, and take some basic measurements. The power supply is meant to be plugged into an AC outlet. It's not a portable DC source like a battery. Internally, the power supply is rectifying or changing the variant AC supply voltage to a DC voltage value desired by the operator. There's a power button on the left-hand side and an indicator LED. This DC power supply won't supply DC power if it's not plugged into the wall or if the power button is off. It is a recommended practice to turn off the power supply when making circuit modifications. Develop good safety habits now. The Tenma triple output DC power supply has 3 outputs. I bet you didn't see that coming. There's an adjustable A pair, an adjustable B pair, and another fixed pair. All the way to the left is a single jack that serves as a ground reference. The 2 adjustable supplies go from 0 to 20 volts. Some versions of the same power supply go from 0 to 24 volts. The fixed pair always remains at 5 volts. Again, the A and B pair are adjustable. What's really neat is that they are independently adjustable. The A pair is controlled via the 2 knobs that say A, and the B pair is controlled via the 2 knobs that say B. Even if you have difficulties distinguishing between the letters A and B, the adjustment knobs are color-coded to the matching pair. The A knobs and outlets are this nauseating shade of pastel green. The B knobs and outlets are this nauseating shade of pastel pink. We'll discuss the function of the knobs when we complete this orientation. Notice there are 2 analog needle meters, one for voltage and one for current. In between them is a selector switch with a pastel green A and a pastel pink B. If I'm using the A terminals and my display selector switch is set to A, I'm really reading the output voltage and current this DC power supply is producing. If, however, I'm using the A terminals, my display selector switch is set to B, I have no idea what the A terminals are producing because I'm not reading them. Don't do this. You wouldn't drive to your school and look at your cell phone the whole time, would you? It's dangerous because you're driving blind if your meters aren't reading the terminals you're actually using. The analog needle meters are not accurate by any means. They're present just to get you in the right ballpark. You must use a DMM to verify and accurately measure the voltage and current produced by the DC power supply. In the upper right, there is another selector switch that determines the relationship between the A and B pair of terminals. This discussion might be a little above our current level of understanding right now, but realize voltage sources can be hooked in series or parallel relationships just like resistors. We saw a set of series opposing and series aiding voltage sources in our example problems. When the selector switch is in the independent position, the A and B terminals are exactly that, totally independent of one another. If you switch over to parallel, A and B are placed in parallel with one another, with the same output voltage, however with an increased output current maximum. If you switch over to series, A and B are placed in series with one another, with increased output voltage and the same output current. We'll return to a more complete discussion of voltage sources in series and in parallel when we discuss respectively series and parallel circuits. For right now, let's just keep these 2 pairs of terminals independent from each other and independently adjustable. Obviously, the A and B voltage knobs increase or decrease the associated pair's voltage between the 2 terminals of interest. What do the current knobs do? If you're familiar with Ohm's law, you realize current is a dependent property of voltage and resistance. This is true. However, the current knobs simply adjust the maximum current an associated terminal set can supply. This is the current limit adjustment. The maximum current capable of being supplied by the adjustable A and B pair is 0.5 amps, or 500 milliamperes. And this value can be adjusted downwards from there via the associated current control knob. In the case of the fixed 5-volt output, it says its limit is fixed at 2 amps. This is incorrect. Be aware of erroneous labels and erroneous data sheets. You should be able to use an ammeter to figure out the maximum current this terminal set is capable of supplying. Either way, these current limits exist because of safety considerations regarding Ohm's law and real circuits. We'll return to a more in-depth discussion of circuit protection devices like fuses, circuit breakers, and overloads in later lectures, but realize in effect, all these devices are doing the same thing. They're preventing current from reaching high values for long periods of time. Understand mathematically, a 0 ohm resistor placed across the terminals of a voltage source of any magnitude would theoretically produce an infinite amount of current. This is obviously never going to happen because resistance is never truly zero and current is never truly infinite. Recall that power is the product of voltage and current, and if our device was truly capable of providing infinite current for a constant voltage value, this means this device would be infinitely powerful, an obviously unachievable device. Consider, however, very small resistances, let's say on the order of 50 milliohms, placed directly across the terminals of a 12-volt battery. 12 volts divided by 50 milliohms would yield a current of 240 amperes. This happens momentarily in applications like starting a car, but is not ordinarily a sustained current. If a 50 milliohm resistor was drawing 240 amps of current continuously, the power supply will be supplying 12 volts times 240, or 2,880 watts continuously. And the 50 milliohm resistor would in turn be dissipating 2,880 watts continuously. This resistor, dissipating power in excess of 3 common household toasters, would melt rather quickly, and before doing so, would glow and burn and set other things in close proximity in fire. This is to generally be avoided in lab environments. Consider, however, a power supply with 2 modes, constant voltage mode and constant current mode. Critical to your understanding of the constant voltage mode is Ohm's law. If I decrease resistance and keep voltage constant, current will increase. At a certain predetermined maximum current, the power supply switches over to constant current mode, and the current never rises above the predetermined maximum because the power supply progressively decreases its output voltage when it experiences incredibly low resistance. Critical to your understanding of the constant current mode is again Ohm's law. If I decrease resistance, I must decrease voltage when my current is limited to a constant amount. Are you recognizing a certain pattern with Ohm's law? A technician without Ohm's law, you're like a Viking without a battle axe. Consider an adjustable resistor hooked up to this 12-volt power supply that is limited to 300 milliamperes. What is the current draw when the adjustable resistor is set to 1.5 kiloohms? Ohm's law states that current is equal to voltage divided by resistance. 12 volts divided by 1.5 kiloohms yields an expected current draw of 8 milliamperes. 8 milliamperes is well within our 300 milliampere limit, so no problem. This power supply is in constant voltage mode. Now adjust our adjustable resistor to 400 ohms. Ohm's law again states that current is equal to voltage divided by resistance. 12 volts divided by 400 ohms yields an expected current draw of 30 milliamperes. 30 milliamperes is again well within our 300 milliampere limit, so again, no problem. We're in constant voltage mode. What if we were to decrease the resistance of our adjustable resistor to 30 ohms? Ordinarily, what would be the current draw for a 30 ohm resistor hooked up to a 12 volt source? Via Ohm's law, current is equal to voltage divided by resistance. 12 volts divided by 30 ohms yields an anticipated current draw of 400 milliamperes, in excess of our current maximum of 300 milliamperes. If again, via Ohm's law, voltage equals current times resistance, the output voltage is simply lowered to keep this 300 milliampere maximum. 300 milliamperes times 30 ohms yields a new output of 9 volts because we have entered constant current mode. What if we really did want 400 milliamperes of current draw though? We would simply adjust our current limit upwards to 400 milliamperes. Via Ohm's law, current is equal to voltage divided by resistance. 12 volts divided by 30 ohms yields a current draw of 400 milliamperes, and now we are just inside constant voltage mode. Any further decrease in resistance would push us into constant current mode, where in this case our current would be limited to a draw of 400 milliamperes. Inside the constant voltage mode, current increases to the maximum with decreasing resistance. Once it's entered constant current mode, Any further decreases in resistance will result in decreasing output voltage to keep the current constant. For our power supply, when a pair of terminals enters this region of maximum current, it indicates so with an LED. In the case of the A and B pair, the LED says constant current, and the fixed 5-volt power supply indicates it is in overload. Having discussed this, ordinarily power supplies are run in constant voltage mode, and constant current mode is typically used only as a safety backup. In the event of an errant short, a power supply simply enters constant current mode to keep the short from becoming a toaster. Additionally, this independently adjustable current knob could be used as a fail-safe limit for sensitive electronics components that need to be protected against high current values. The current limit is simply adjusted at or below this maximum value, and the power supply will not exceed it. Let's use the Tenma triple output power supply and set up the A terminals to produce a 10-volt differential between its two terminals. The display selector switch is set to A, and then I just spin the voltage knob on A until the needle meter indicates it's close to 10 volts. Notice the current needle meter is reading 0 amperes, as expected, because it's not supplying current. Is the needle meter accurate? Kind of. My DMM and voltmeter mode indicates it's actually 10.4 volts. Keeping the DMM and voltmeter mode attached, I just dial it down a scotch and my DMM shows that I'm at 10.01 volts. Leave it. Don't touch it. Any further fiddling with this knob is just going to waste time and infuriate your lab partner. 10.01 volts is 10 volts. If I accidentally had my display selector knob reading the B terminals, I might be tempted into believing a contradiction exists. The needle meter indicates something close to 20 volts, but the DMM in voltmeter mode is reading 10 volts. Obviously, I'm on the wrong set. I can measure the B pair using the DMM in voltmeter mode, and it shows 20.73 volts, resolving my contradiction. While we're at it, let's check out the third terminal set. We're observing 5.02 volts, regardless of the position of the knobs, because this is the fixed 5-volt supply. Let's get our A voltage knob close to 20 volts using just the needle meter and check it out using the DMM in voltmeter mode. It shows 20.78 volts. Not bad, but we could be closer. If I was to swap the reference lead of my voltmeter such that it is measuring the voltage differential between it and the negative terminal, it would indicate that the negative terminal is 20.78 volts lower than the reference lead by placing a negative sign up front. Up to this point, realize we've been discussing the DC power supply without reference to anything like ground. Let's start including a ground reference, but before doing so, let's turn off our power supply and do a continuity check with our DMM and ohm meter mode. Again, the power supply is off, and I would never ever do a continuity check with the power on. Is the ground lead in any way, shape, or form connected to any other lead? The answer is no. Any combination of terminals in the ground connection indicates an open circuit. All our previous measurements have been without reference to ground. These terminals are independent from ground. While we're at it, let's do a continuity check between terminals. The resistance between the two A terminals is 18.62 kiloohms. This is the resistance of this source while it's off. It's for this reason all resistance measurements of individual components are taken when the power is off and they're removed from the circuit. Anything still in the circuit with this power supply, even if it was off, would be in parallel with this 18.6 kilo ohm resistance, hopelessly rendering inaccurate any values you obtain. One more comment about these resistance values we've obtained using the DMM and ohm meter mode. Notice how smooth the transition from voltmeter mode to ohm meter mode was. At no point do we make the unforgivable error of taking resistance measurement with the power on. I know a lot of material is hitting you at once, but eventually, strictly through repetitive exposure and me repetitively hammering you with a function, leads, range, and placement checklist every time you use the DMM, your lab is going to go this well too. The ability to quickly, flawlessly and safely transition from voltage, resistance, and current measurements using common instruments like the DMM is the primary skill you must develop during a supporting hardware lab. It is something that cannot be learned by watching an online lecture and must be practiced and applied in real life. This is a juggling act that is only going to get more and more complicated with the more and more multicolored balls I throw at you. Right now, we're only juggling two, the voltmeter and the ohm meter. We're going to quickly add a third ball to the mix, the ammeter, with its own unique considerations. At all times, you got to keep all balls in the air and never let one drop. Concepts aside, your ability to correctly and safely employ competent instrumentation is an extremely valuable skill set. Turning the power supply back on and returning back to voltmeter mode, you notice the voltage between the A high lead and ground is kind of nonsense because there's no association between ground and this isolated set of terminals. In this case, the 20.78 volts of the A terminals is only with respect to each other. If, however, I tie the negative lead of the A source to ground, the positive lead is now 20.78 volts higher than ground. Again, the difference between the two terminals still exists. It's just that they're now referenced from something else. In this case, conventional current can flow from the positive terminal to the negative terminal or the ground since they're at the same potential if a conductive path existed. Now, let's try a positively grounded DC power supply. In this case, the positive lead is tied to ground, and there exists no differential between the positive lead and ground. However, there still exists a positive 20.78 volt differential between the negative lead of the source and the positive lead when the negative lead is used as the reference. However, when ground is used as the reference, it shows the negative lead is now 20.78 volts below ground by placing a negative sign up front. The same magnitude exists, it's just that the conventional current will now flow from either the ground or our positive terminal since they're at the same potential to the negative terminal. Alright, now that we're familiar with voltage adjustments and ground references using our DC power supply, let's set up our first circuit using our output voltage of 20.78 volts. Take your time and look at this. Very rarely is a circuit so clearly indicative of such a perfect combination of equal parts stupid and dangerous. Yes, this is a complete circuit, but it is a circuit of such extremely low resistance that we would ordinarily expect a constant voltage power supply to deliver extremely high dangerous current because the resistance is so low. Obviously, I'm intending this circuit to demonstrate the constant current mode of our power supply. In the face of such a heinously wrong event, even if I had the power supply set to 20.78 volts, the power supply instantly pegs at the maximum current, in this case around 200 milliamperes. Notice the power supply indicates we are in constant current mode or overload conditions with the LED. Additionally, notice the needle meter indicating voltage is not 20.78 volts anymore and has dropped into unreadably small territory because the voltage necessary to produce a current of 200 milliamperes through such an incredibly low resistance path is so small. If I wanted to, I could adjust the maximum current supplied upwards. I could do so with the current adjustment knob. Word of troubleshooting advice. Short circuits aren't as glaringly obvious as this one, and very often they're just indistinguishable errant wires. If your power supply instantly pegs at the maximum current in an overload condition, there exists one of three possible occurrences in increasing levels of probability. 1. You are operating in the constant current mode and you're aware of this. Carry on. Your current limit is set too low. Readjust as necessary and carry on. And 3, you have a short circuit and you need to immediately turn off the power supply and fix the problem. Again, it might not be painted neon green and be easily identifiable, but it's in there somewhere and it's your job to find it. Again, all paths must have an appropriate amount of resistance to control current. Look for errant low resistance paths. If you're using a protoboard in a lab environment, make sure you're using it properly. If you're in an industrial setting, look for faulted wiring or some conductive element bridging a connection. Again, ordinarily power supplies are operated in constant voltage mode under the current limitation. Constant current mode is typically just employed as a backup. As a bit of advice, check the power supply output voltage for every load configuration and don't just assume its output stays constant. Realize output voltage could vary widely between unloaded and heavily loaded conditions for reasons I'll explain when we get to the series DC circuits lectures. The analog needle meter is there just to get us in the right ballpark. Always use your DMM and voltmeter mode to verify output voltage for loaded conditions and readjust as necessary. Alright, this is really as far as we can get without introducing the ammeter or going into experimental verification of Ohm's law, and kind of wraps up our introduction to basic power supplies. Later lab practices lecture will employ the DC power supplies as a supporting cast member to discuss these topics and more. In conclusion, this lecture took a look at basic DC power supplies, reviewed voltage, discussed ground using a common frame of reference, and learned to use a power supply with or without a ground reference. Additionally, we discussed the differences between constant voltage mode and constant current mode for DC power supplies. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.